Hi, everyone. My name is Gideon Mendels. Today I'm going to talk about running effective machine learning teams and specifically around common issues, challenges, and solution. So before we dive in, if you're not yet convinced, I want to spend just a few slides on the deep learning revolution. So indeed, it looks like everyone's been talking about machine learning and deep learning these days. And indeed, if you look at mostly academic benchmarks, we see these methods outperform significant benchmarks and previous applications. And for today's talk, I picked just a couple of examples to give you an idea. So the first one I have here is the ImageNet dataset. So ImageNet is a computer vision dataset. It consists of images, and each image would have an object in it, anything from a common household object or even a dog breed. And what you can see here on the chart, if you focus on the second bar on the left, is in 2012, the first implementation of a deep learning model called AlexNet was submitted and immediately shaved 10 absolute percent points from previous year's submission, the 2011, which was a traditional computer vision algorithm. And for a problem which is considered pretty difficult, this is very significant. And as the years continue, better neural network models have been submitted up until 2015 that Microsoft releases ResNet and essentially managed to beat the human performance on this problem. The second example I picked is from a completely different domain, the switchboard dataset. So switchboard is a speech recognition problem. Given a speech utterance, we're trying to predict a sequence of words, so traditional speech to text. And as you can see in the mid-2000s, the research community was really struggling in improving results, and the word error rate results, which is how we measure these models, pretty much leveled out for a few years. And in 2012, so very similar timeline to when AlexNet was submitted, the first application of DNN, in this case on what's called the acoustic model, so one piece of the ASR application was submitted and managed to again improve by 3 absolute percent points. And then as the years go by, the results continue to improve up until, again, Microsoft in 2016 managed to reach human parity on this problem. And a lot of you might be skeptical because you've used Siri or Alexa, and it's hard to say they reached human parity. But just for the example here, switchboard is considered a fairly easy problem. It's only about 200 speakers, so there's no challenges with accents and OOVs and these kind of things. But what we see in the industry that companies like Google that know how to leverage these models are seeing significant ROI from this. So what this chart shows is essentially the count of models in the Google source code repository. And you can see, obviously this chart ends in 2016, but I'm pretty confident saying that this exponential growth has continued since. But I think one of the interesting parts is we're seeing these models not only in traditional machine learning problems like vision and speech, but pretty much across the Google product portfolio. So apps, maps, and even things like drug discovery. So indeed, we live in this machine learning pioneering age, and it's really, really exciting to be part of it in conferences like these. But while these academic benchmarks have kind of beaten, most companies are still struggling extracting business value out of machine learning. And at Comet, we believe that's because two main things. The first thing is companies are trying to solve the wrong problems with machine learning. And the second thing is we're trying to use the processes and the tools we know from the software engineering world for machine learning. And these things are very different, and I'm definitely going to spend more time on that. So if you're in your organization, you're thinking, how can I create business value out of machine learning? A common mistake we see is essentially giving a data scientist this autonomy to figure out what to solve. Now, while a data scientist would know which problems are feasible to solve with machine learning, they might not have a good idea of what problems are actually valuable for the business. And on the flip side, if you go to someone more on the business side, they know what's important, but they have no idea what's feasible with machine learning. And some people have this notion that AI can solve everything. So the key here is to bring these two personas into the same room and together find this golden intersection of where problems are A, feasible, and B, would bring significant ROI for the business. But even if you kind of figure out these problems, there's a few things you have to make sure you're doing. The first thing is start small. And in fact, at Comet, we recommend to kind of Fortune 500s that we work with to pick a portfolio approach. So instead of just trying to solve one thing, pick 4 or 5 problems, of course, depending on the size of the problem and the size of your team. But in this way, you're de-risking your chance of failing on your machine learning problems, because even if 3 out of problems fail, you still have 2 left. And start simple. Start with something that's easy. Spend 3 to 6 months on it. Usually, with a simple modeling approach before diving into sophisticated techniques. In most cases, you would have some notion whether there's signal in the data, whether you can move or do something better than that. And of course, at that point, you're welcome to jump into like fancier techniques and things like that. So the thing is, even if you pick the right projects and the right problems to work on, there's many, many other challenges. But instead of kind of just walking through bullet points, I'd like to share a short story from the time I spent at Google building these models. So the problem we were working on was hate speech classification. So basically, given a YouTube comment, try to detect whether it has hate speech or not. So it's a typical document classification problem. It's a binary classification problem. And at the time, we had a fairly small data set, so only a few thousand labeled comments. And the goal was to outperform the production model. So the team already had a model that's been running for a little over a year. So if you think about my example before, this was something we know brings ROI to the business, and we know it's feasible because we already have a model in production. And when you're trying to outperform a model, a good place to start is, well, what's that model that we're trying to outperform? And to answer that question, you need to have a few pieces in place. The first thing is your training data, right? And in our case, we actually had a very hard time finding the training data because we had 10 different versions of it, each one with a different feature, normalization, extraction, cleanup, things like that. And no one was actually sure what was the version that the production model was trained on. The second thing is your hyperparameters. So in our case, the hyperparameters were actually fed as command line arguments to the scheduler, so they were lost forever. Another piece is the training code, which we had checked into the Google source code repository, so that was fine. Then you need the results. So we actually found someone kind of quoting the accuracy in an email, but we didn't know any other important classification metrics like precision, recall, F1, and so on. And then the last piece is, of course, the model binary, which we had because it was served behind an API. So we spent a lot of time. We tried to reproduce the production model. We could ping the API, so it was a little bit easier. We did some detective work. We figured out all the pieces, and we got to 95% accuracy, which was pretty much what was stated in the email. So, not bad. Again, this is a binary classification on a balanced data set, so chance here is 50-50. But before we wanted to move forward and try a fancier technique or something that might do better than this, we said, let's baseline the problem first. Start with something simple, so we'll have an idea of how hard this problem is before we kind of dive into a new research avenue. So if any one of you have done NLP before, we picked really the NLP 101, the most basic approach here. We used n-grams. So n-grams is essentially a way of mapping words into tokens. So if n is equal 1, we're talking about unigrams. So we replace the token with an ID of the dictionary. If n equals 2, bigrams, we do it in pairs, and so on and so on. On top of that, we added some simple NLP methods. So we use stemming, which is a way of reducing your feature space by mapping words that's coming from the same stem into the same token. So in this case, processing and process will map to the same word. We use stop words removal, which in our case, so stop words are essentially usually the most common words in the language, like it, are, we, they. And in our case, they have very little signal or value when trying to predict hate speech. And finally, we use TF-IDF, which is a normalization technique that allows us to treat short and long comments in a similar way. And on top of that, we picked logistic regression, so very simple classifier. And we spent a few weeks or a little bit over than that building this model, which is pretty simple. And what we found was pretty surprising. So our production model, which was a fairly fancy approach at the time, had 95% accuracy. We trained our n-gram model, and we actually beat the production classifier with a really simple approach. So at this point, we realized, okay, we might have an issue here. How does this happen? How does a team spend a year and a half on a model, a new research avenue, when literally the most basic approach in NLP beats the production model? But we weren't discouraged. We figured out okay, if we can do this well with unigrams and n-grams, we can probably do better. We went to kind of like the academic literature, and we found this paper using CNN, so very similar to AlexNet actually, on text classification. So this is by one of Jan LeCun's students, so one of the fathers of deep learning, and at the time was state of the art. And one of the things that were compelling here is they also had pretty good results with n-grams. So that's the second row there in that table, but they managed to beat that with convolutional neural networks. So again, we went into this detective work. We had to figure out their data, their hyperparameters, their code, all this information, trying to reproduce this paper, which was pretty challenging. And we had to go back and forth with the authors. But at the end of the day, we managed to retrain this model. And unfortunately, even that model does worse than n-grams. And in fact, when we retrained our n-grams pipeline on the data set from the paper, we actually managed to beat the CNN result as well. So a lot of challenges there. But if we kind of summarize this, what are the challenges we've seen? The first thing, we didn't have a team-wide process or methodology to run the research phase of things. Second thing is lack of visibility. So we didn't know what experiments ran, models, the rest of the data science pipeline. It was completely, everyone was working in a very siloed way, and zero reproducibility. So every time we tried to reproduce a model, we had to spend time figuring out all these different pieces. And quite truthfully, if we had a way of doing or getting reproducibility, we would probably save a year of work. And this is a team of about 5 or 6 people. So at this point, you might ask yourself and say, well, I think this is a solved problem, right? So I split this part into 2. One is the methodology, and the other side is more on the collaboration and visibility. So when it comes to methodology, you say, well, my company's been building software for years. There's these things called agile and Scrum. You should really take a look. They're great. But in fact, when we go to machine learning, these methods fail pretty miserably. So the thing is with machine learning is a process that kind of by nature is uncertain. So everything that talks about planning becomes very, very challenging. And I picked Scrum just as an example. So this is kind of like the traditional high-level overview of the Scrum development process. And we start with usually what's the product backlog, right? The list of features that the user have been asking for. And if you remember what I talked a little bit earlier is we can't build every feature the user is asking for because some things are just not feasible with machine learning. And even if we kind of clean that backlog up and we're trying to do some sprint planning, how do you do that? How do you know how much time are you going to spend on finding the data, cleaning the data, training the model? We never know if a project would take 2 months or 2 years. So planning becomes very, very, very hard. So hopefully this gives you a little bit of an idea of why it's challenging to apply these methods. And I'll explain a little bit later on kind of like best practices and how to do that well. So if you look at the machine learning development process, and this chart actually came from a Microsoft paper, kind of going through the different stages here. So we start with the model requirement. We go into data collection, whether it's within our company or outside, data cleaning, which is the fun part, as we all know, data labeling, and then we go into the modeling phase. So feature engineering and model training. And this arrow kind of shows that this process is iterative. We can spend weeks, months, even years on this. And then we might go into some evaluation looking at both the stats metrics or the business KPIs. And what this arrow on the top shows is from this step, you can actually go back to anywhere you started from. So you might completely revisit the model requirements. You might realize you need more data. You might realize you need to label more data. So this could take forever. And again, because there's so many feedback loops, experimentation is necessary, which why it's really hard to use things like Scrum. And then the second part, more on the visibility, collaboration, and reproducibility. I'm sure you all heard about a tool called Git, and it's really, really good. You should take a look at this. And organization has been using it for years to manage source code. And Git is a very flexible tool, but I picked kind of one example of how you might try to use Git to solve this problem. So if I kind of walk through line by line, very simple. I'm creating a new branch. I'm calling it new experiment. I'm running my Python training file, pathing in a path to my data set, some hyperparameters, and I'm being very careful. I'm actually saving or passing a file pointer, so I would save the results to the right file. And if you think about our story from Google earlier, it looks like we have all the pieces in place, right? Code, pointer to the data, hyperparameters, results. This looks somehow promising, adding the results and pushing the branch. But then if you do this and you go to GitHub, you usually end up with something that looks like this. So you have a long list of branches that has no semantic meaning, so it's impossible to kind of walk through them and understand which one is important. And second, even if you find the right branch, in our example, you might have multiple training files, and you don't know which one generated the right results file, so tracking these dependencies is pretty challenging with a tool like Git. And that's actually not that surprising because these tools we've been building for the last 30 years are built for software engineering. And even though machine learning has code, which is a big portion of it, it's still just one piece of the puzzle. So how do we solve this, right? That's the interesting part. So when it comes to methodology, we picked one example from Andrew Ng, another father of deep learning, and he gave a talk about this topic, and what his team at Landing AI is doing is one-day sprints. So I'm sure every software engineer here is like, ooh, one-day sprints, that doesn't sound like fun. And indeed, that's, it's a little bit of a difference. So basically what they would have done, they would work throughout the day, running, code their models, do some analysis, run models overnight, and then come back in the next morning and revisit the results. So we're condensing the entire process into one day, and then you can kind of have a better idea of how to drive research forward. The second side is more around visibility, collaboration, and reproducibility. Is, as you might have guessed, you need a dedicated experiment management platform to do so. So an experiment platform will really solve all these problems because it's designed for this purpose. First thing, you'll have full team visibility to all parts of the modeling lifecycle. You could track and compare metrics, data, hyperparameters, but also information about the underlying machine, like GPU statistics and more. You'd be able to reproduce every experiment. And finally, you have a central platform where teammates can collaborate. So every user would have their own account. You can share. You know who ran what models, and so on. So this is just one screenshot to give you an idea how this might look. So if you can look on the left, we have full tracking of our code, hyperparameters. In this case, we can look into the training data itself to realize why the model is doing better or which predictions it's failing in. We have a one-click button to reproduce. And per that question earlier, real-time tracking of your models while they're training. And like was discussed in previous talk, the top companies out there are actually building these platforms internally. So Uber has Michelangelo, Facebook has FB Learner. But if you're not one of those, you can actually find solutions out there in the market. So if you're looking for an enterprise solution, you can look at things like Comet or open source ML Flow has been discussed before. There's also Trains and Sacred that are available on GitHub. But the one really exciting thing is, once you solve visibility, collaboration, reproducibility, and tracking, it opens this whole new realm of new things you couldn't have done before. So if you have a central system of record of all these pieces, suddenly you can start looking into that data, and there's this new layer of meta-learning on top of it. So things like hyperparameter optimization with intelligent early stopping that looks at your previous experiments, debugging of models, so not only from the code side, but also looking at predictions and predictions over time, explainability, so incorporating tools like SHAP and Lime, and finally meta-analysis, visualizing your hyperparameter space in aggregate, and not just looking at a single experiment or comparing a few of them. So just a final note here. At Comet, in the near future, we believe these tools will become standardized, and your adoption or your organization adoption will impact, A, your team productivity, your ability to extract ROI from machine learning, and help you hiring good candidates. And finally, if you're trying to use AI as a competitive advantage, it will ultimately affect that as well. So that's all for today. Thank you so much. I'd love to answer any questions now.